starting to get to an interesting part of this course, I think. This morning we discussed the classical, I hope I have some dry chalk, here we go. Classical compact groups. Spent 2 lectures on this actually. There are 3 infinite series. This is the one I want to focus on. There's some exceptional groups as I mentioned, but I will not focus on them. And the 3 infinite series are the orthogonal group, ON, unitary group, UN, and the unitary symplectic group, USP2N. And we have seen we have studied the action of a standard action of ON, and in fact SON2 we can restrict to determinant 1 almost in every case here on the sphere Sn minus 1. So we look at it, this is the unit sphere in Rn. So it's a beautiful picture. The orthogonal group or special orthogonal group acting on the sphere. And action is transitive. It means it maps 1 point, although all others if you wish. Let K be, in this case, ON, it's compact, so it justifies the notation K. And therefore, for every point, in the sphere, so a vector of length 1 in the Euclidean space, in the standard scalar product, point V, well, let's call it x0, it doesn't matter which one it is, in the sphere, the orbit is the whole thing. This equals the sphere. So remember our language, Sn minus 1, the sphere, is, what we say here, is K homogeneous. That's standard language in this business. And so that means that the sphere, Sn minus 1, is K modulo the isotropy at any point you chose. We chose some point here. We chose, for example, a point to make it easy. Let's choose at the point 1, 0, 0. Maybe, I don't know, that's a column vector or a row vector. Let's make it column vectors to make it consistent. So 1, 0, 0. Yeah? And the usual notation, if you don't want to make explicit what this is, I always write this as K modulo L. And here we drew a picture of L. And let's make K, I said K equals ON, but let's make K SON to make things easy. SON. And so we don't have to worry about determinants. And this looks this way, and this block here is SON minus 1. That fixes the first vector, if that's, I don't know, the North Pole or whatever it is, and then anything else works, but of course it has to be orthogonal matrix, so that means that these things have to orthonormal. And so we find a rather very good inductive way of studying spheres and of studying these things. Namely, you have a picture of K, which is S-O-N, and you have the isotropy, so I'm drawing the picture of the quotient K modulo L, which is S-O-N modulo S-O-N minus 1. And so you have a sphere, this is the sphere, S2 and Sn minus 1, and you have it realized as a homogeneous space of K with isotropy over base point x0 with isotropy SL equal SON minus 1. So this is a beautiful way of studying spheres and studying the compact orthogonal group SON. This is the basic picture. You pay your money and take your choice. If you want to know about spheres, usually you want to know about orthogonal groups, because the sphere is really defined in some sense about orthogonal groups, just as in this picture, in the lingo of mathematics. This is a very natural principal bundle over the sphere. This is more or less the thing that must be studied if you're studying spheres. And so it's a combined thing. You either look at L invariant things on the group, or you look at properties of the sphere. So that you keep in mind when you're looking at orthogonal groups. And now let's look at unitary groups. Well, the unitary group, so the unitary group UN is the group of, let's write it down here, the group of T and GLNC, such that if you look at the standard Hermitian product, I introduced this morning, I reminded you of it, the standard Hermitian product is preserved by this action. Naturally for all V and W. And this morning I pointed out that you know that it's not hard to do. This Hermitian form in vector notation, H of VW, is, maybe the way I wrote it is V transpose W bar. I don't particularly like that way, but I did it that way because it's very natural. In a basis, it's the sum of Zi Wj bar. Wi bar. I mean, it looks like that, so I put the bar here, but I don't like to. I actually prefer putting everything in one place. But anyway, that's the way it looks, the standard Hermitian structure. We talked about it at great length this morning. And so the equation is, the equation, well, you just get, so H of T V T W is V TV transpose TVW bar, and now put that in the middle, so that's V transpose T transpose T bar W, and this has to be the identity. This has to be true for all W, so this has to be the identity, and that says that T transpose T bar is the identity, and so this says that T equals T bar transpose inverse. Very interesting. You see here three evolutions: antilinear evolution bar and transpose inverse, which are really mysterious evolutions. So it's very interesting. that's the defining equation for the unitary group. And of course, the matrix, a matrix in the unitary group, a unitary matrix, let's call it U in the unitary group, the matrix, just as exactly in the orthogonal case, you have a unitary basis. You just have to have a unitary basis of the vector space, and the unitary basis statement is that T EI well, norm of TI squared equals 1, and T of EI is usually perpendicular, but there's a case when it's not, and that's when they're equal. So that's what I call that basis a unitary basis. Okay? Some people even say orthogonal basis with the unitary structure in the background. But when I say orthogonal basis, usually I'm thinking in terms of these real groups, whereas here this is the unitary group. So the equation, as you know, as we've written down this morning, is well, let's write it down. I mean, oh, I'm sorry, I wrote T, so let's even be precise. Let's put it a unity here. U stands for unitary. Right. And the condition is we have the condition here. It is U equals U bar transpose inverse, and that means that's the same thing as U is equal to the fixed point of some involution, which I call sigma, where sigma of U is whatever this is, U bar inverse. Okay, that's it. That's the way the matrix looks, and so on. And now U. Of course, we know U of U of V, norm squared, equals 1 if V is in the sphere of radius 1. So if V has norm 1. So this says that the unitary group UN acts on the unit sphere, in Cn. Yeah. So this sphere, let's call it I don't know. It's 2n minus 1 dimensional, and if you take usual coordinates z1 through zn in standard coordinates for Cn, maybe with transpose to make it a column vector or something. I don't care. This is equal to z1 norm squared plus Zn norm squared equals 1. And if you just break this up to what it really is, this is the same thing as x1 squared with xn squared plus y1 squared down to yn squared. These are the real one here, where zi is equal to x, z alpha is equal to x alpha plus I alpha. So it's the standard sphere in the real background real space of this complex vector space, but we wrote it in the Hermitian way that we discussed this morning. And obviously it preserves the norm, so it preserves the sphere. And you use the usual thing. So you check just exactly as we checked it for the unit sphere over the orthogonal group. I'm hoping I have some chalk. Unit sphere of the orthogonal group, the orthogonal group acting on the unit sphere is you just take the base point which is the basis vector E1 in the unit sphere, right? and you are given, suppose you are given another point, given, I don't know, let's say V in the unit sphere. So it's the usual picture. Let me draw what I was talking about before. I don't know where that base point is. Maybe it's over here in the picture. This is over here, and you're giving some mysterious point here, V, and you want, and this is also in the unit sphere, and you want a transformation U, which takes it that to that. So let's see if we can build it. So E1 has to go to U. So we start to build the matrix U by, and we just put in the first column where E1 goes. We put in the vector V, so V1 through Vn. This is a vector of length 1. And so now we do the standard, what is called, of German basis, Basisergänzungssatz. What is it? How do you say it? Basic completion. I mean, you start with a vector, you go to the orthogonal complement, you take a basis of that, and so on, and so on, and so on, and so on. Okay? So that means you can fill this out to En using extent or your unitary basis extension. So we just fill it out, and so you can find then that whole thing is a unitary matrix, and it takes E1 to the right point. And so the theorem is that the group UN acts transitively on the sphere S2n minus 1. And so does, and even, it's easy to see this has nothing to do with the determinant. In fact, it's the same as true. Same is true for the determinant 0 thing. So S-U-N. You just check it. Okay. So groups act on spheres, these classical groups. And and it's a very important thing. So if this is K, then we have the sphere. We take x0 to be equal to the base point E1 in the sphere. So the same thing here. And so the sphere itself is K modulo right action of the isotropy. And I write this as K modulo L. If anything I write in the literature, if I write K or L, it's always compact. Or complexification of compact. Very close to compact. I use that notation also. Always. And now what L looks like, it looks like this. It looks like, it has to be in the isotropy, so it looks like something like this. Say this it does this. And it looks like that, maybe. Let's see here. Oh yes, that's good. That has to be in there. That's good. That has to fix this point. And then here we have SUN minus 1. Because the determinant is 1, so that's 1, and so that has to have determinant 1. And so what it says is that this thing is wonderful. This is equal to SUN modulo SUN minus 1. You're going to get tired of me. You might go to sleep at night thinking of my picture. You have the sphere, SN minus 1. You have the picture upstairs of the unitary group, UN. This is equal to, or SUN, I decided to make it my favorite one, SUN modulo the right action of SUN minus 1. Every orbit is G modulo isotropy, right action of the isotropy. This picture is is if you have a base point x0, which we had above, in the group. Here's the identity. Here is L, which is SUN minus 1. And you have the right action. So this is, in fact, if you take anything up here, little k, then what you get in this fiber here is little k times L on the right. I recommend that you understand that, because most people who fool around with this stuff don't, and they really don't understand anything if they don't understand this picture. I guarantee you. So this is a beautiful picture. You have your pay your money and take your choice. This is a quotient of a group action, namely the L action of the group on the right. To get the sphere, study the sphere with the groups or study the groups with the sphere. There's a very, very close relationship to groups and spheres. Okay. For those of you, I know some people here have understood the topology. You think the sphere doesn't have anything interesting in it. If you look at it, right, you don't see very many interesting topology. But if you learn topology, that means algebraic topology, which you theoretically learned a little bit. The point is that there are non-trivial higher homotopy groups of the sphere beyond dimension. And in fact, the only way to understand this stuff is through basic results of Bott, B-O-T-T, Raoul Bott. Not very old, but fundamental results of Bott that relate higher homotopy groups of spheres. Really, he's thinking in terms of the unitary and orthogonal groups and so on. Now, actually, to maybe an interesting exercise, but you can see it rather easily. So maybe I have to think what the numbers are. So let's make a number. Let's see here. SP4 C acts on C4. And of course, you should check, I mean, this is a complex group, obviously, and you should check what its orbits are. It's pretty interesting. But more interestingly then, USP4 then acts, because it preserves the unitary norm, on the sphere in C4. On the sphere in C4. It's the unitary symplectic transformations, and the sphere in C4, the unit sphere in C4 is C4, unit sphere in C4. That's real 8 dimensions. So this acts on the 7th sphere. All right? You know what we could do? This acts on the 7th sphere, that's true, but let's even do it smaller. This is the point 1. Point 2, I usually go too complicated. Let's look at SP2. 2 times 1 is 2. So SP2, see, it acts on, this is good, on C2 because it's in GL2, and USP acts, USP2 acts on the sphere in CO2, there we go, acts on the sphere in there, and that's S3. Okay? And in fact, you can check, once I've told you this, you just start thinking a little bit, and you can show, now I got to get the numbers right here. USP 2N acts on, now somebody's got to help me. So acts on acts on, okay, it's easy. It acts on C2N. So and the sphere in C2N is 4n minus 1. Right? Because C2n is R4n, and the sphere is one-dimensional less. So they're very interesting things. It acts on S3. There's a little bit of a joke, and this happens all the time in this theory. This is actually SU2. So there's a little bit of jokes at lower numbers, but these jokes stop when you get up here, and it gets pretty interesting already at S7 and way on up here. So you will see spheres of dimension 4n minus 1 being very special spheres. And the reason is there is this group acting on this sphere, which is the unitary symplectic group SUP2M. It's a very interesting thing. So if you want, let's call this an exercise, prove that this thing acts on this transitively. So in fact, S4n minus 1 is a homogeneous space of all three groups. All three groups. So what are the groups? The real orthogonal group O4n, the unitary group U2n, and the unitary symplectic group SP2n. It's pretty interesting, right? So there's one mega interest. The first interesting sphere in this discussion is the 7 sphere. A lot of interesting phenomena starts occurring around dimension 7. So there's an example of it. So take a look if you can understand this. Okay. Now, the rest of my lecture today is probably only going to be devoted to the unitary group. So I'm going to talk about unitary groups UN, and and probably I'll have SUN. So pardon me if I'm not careful. SUN and their actions. These are very fundamental things, at least for those of you who are interested in applications of mathematics, for example, physics. So we talked a little bit their actions on the sphere, transitive, and so on. Well, the first thing I'm going to start with at a complete beginning step is let's look at U1's action. U1. I mean, you should start with 1. So the U1 action well, we just talked about it on C, on the vector space V, which we know to be, which is C if we take the standard basic. All right? U1 is a 1 times 1 matrix, so U1 is a 1 times 1 matrix, so if we take an element here, which is, say, the unitary element U, then the matrix of U is equal to a 1 times 1 matrix. We think it's trivial, so we have to be careful. Maybe it's not so trivial. Let's see what happens here. What is the matrix of U? What's the condition? Where's the involution? The involution of U is U equals U bar transpose inverse. So the involution is this thing, let's call this matrix U also. U is equal to U bar inverse transpose. And of course, it's a 1 times 1 matrix, so if 1 times 1 matrix is, say, number lambda, complex number lambda, and let's see, that's equal to, as a 1 times 1 matrix, lambda bar inverse inverse, transposable 1 by 1 is no problem. So the condition is lambda equals lambda power. This is the fixed point of the involution, and so we bring it on the other side. It says the lambda in absolute value squared equals 1. I bring it on the other side. Right. Now that's a famous equation, right? That's a famous equation. So we know that lambda is a point in the circle. So we identify U1 with the unit circle. And so the action of U1 on the vector space, so on the vector space, this is the action of U1, not SU1. SU1 is nothing, it's just the identity. The determinant here is of course not 1. So on C, the action is Z goes to lambda Z, where lambda is a rotation, because it's absolute value 1. So that's pretty simple. Okay, 1 by 1 matrix. Okay, let's look at U2. Well, now U2 is interesting, so let's look at the matrix SU2. We can afford to take determinant 1. Here we can't afford it because we just kill everything. So SU2, the matrix of SU2. So what is that? That is the matrices. I'm going to write this as matrices, unitary matrices, such that U equals U bar transpose inverse. And of course the determinant of U equals 1. Okay? And this thing is acting on C2. And if we have a picture of C2, we just say it looks like this in C2. Here's C2. Of course, the origin is fixed because it's acting linearly, but it acts transitively on every sphere. It's hard for me to draw three-dimensional spheres in four-dimensional space, but these are spheres S3 or the orbits. It's obvious, right? It acts transitively on spheres. It's very interesting. So it's very interesting. Well, the quotient, for example, of this is very easily computed because you have a slice and an obvious slice, which is a half open interval, obvious fundamental region of this thing. I'll put it in here. Here's a slice, right? Intersect each orbit in one point. So the quotient is simply, in other words, no, this, what did I have here? This is C2, I'm sorry. C2, the quotient then is, I'll draw it what it looks like really. It's a half interval, a half real number. So the quotient can be identified very naturally with a set of real numbers greater than or equal to 0. Again, it stays inside the algebraic setting that is defined by inequalities. It couldn't be any better. And it's a perfect situation. So Donald Trump would say this is perfect, this situation. So this situation is great, it's cool, and everything's wonderful. Now let's look at the action. So S3, this is the orbit of the unitary group SU2. Times the point E1, all right? And we know that this is then SU2 modulo SU1, we just talked about it, But SU1 is trivial. As soon as you force the determinant to be 1, it's trivial. So this is just SU2. So it says that through this group action that S3 is identified with SU2. Now there's got to be something going on if that's happening, right? So if you are somebody, for example, by the name of Hamilton, I don't mean the American, who's involved in the American government, and it's a very important Broadway play named after him and so on. He's a very interesting person, but I mean the Irish Hamilton, who's responsible for Hamiltonian mechanics, who's responsible for many things. If you're Hamilton and looking at this thing, you should be interested because you found a group inside. You see, this was defined inside. Well, this is a group which is a sphere inside a complex vector space. All right. So you're almost showing that the complex vector space is a group. If you're a physicist, you're very optimistic. Well, it's a sphere, so maybe the whole thing's a group, right? You should be optimistic, but then you should prove and guess and try to prove something, okay? So Hamilton, of course, was looking for a long time, along with others, for the quaternions. He was looking for division algebra. So he said, well, you have R, and then you have C, and then you should have the next thing. And you do have R, and then you have C, and then you have the quaternions, and then you have the Cayley numbers, and that's it, and that's a classification of certain algebraic structures, which you should know about, and I'm not going to teach you. Okay. So that's very interesting, and Hamilton was very interested in finding these things long ago. Not so long ago. He was looking at, he's interested in this group. So let's say that's a group. The sphere is a group. Maybe we should find, let's see here, if I can get this up for the cameras. Let's see if we can find a standard basis. So we're going to write SU2 down as the standard basis. So what did I say? It's a 2 by 2 matrix. So T of E1 should be AB, and T is T of E1, and T of E2 should be CD. But it has to satisfy the involution condition. So sigma T has to be equal to T bar transpose inverse. These things have to be orthonormal. So this has to be a length 1, and this has to be perpendicular to it, and you know here this is a length of 1, here's AB, and of course perpendicular you have almost no choice, and you have some choice, but if you have determinant equal to 1, you have no choice. This thing has to be minus B bar A. This thing has to be minus, you think minus B over A to get the, but it's not, it's minus B bar over A bar because it's the Hermitian structure. So to make this thing really, this is T of E2. It has to be perpendicular with respect to the Hermitian structure, and the Hermitian structure, as you know, is you can just write down. Let's just write it down: Z1 W1 bar plus Z2 W2 bar. This is the Hermitian structure, no problem. And if you have determinant equal to 1, that's the orientation thing. You have no choices for this. This has to be B bar, A bar. You have no choice. So Hamilton's cruising around someplace in Dublin, or maybe he wants to come to Cambridge and be alone. You know, these guys really, we're going to have Brexit now, but we have Ireland, and it's very complicated. Very non-trivial in those other days. This is B bar, A bar. Right. So this is what SU2 looks like. So SU2 is, let's write it down. SU2 is a set of as matrices, the set of matrices A, B, minus B bar, A bar. And now you see this is perpendicular with respect to the Hermitian form. You take this times this bar, that's minus AB, plus this times this bar, that's BA, so that's 0. And this should have length 1. Well, length 1 is the same as the determinant being 1, and we're very, very happy because it is exactly this condition. So you see exactly that this thing is the group S3, is the sphere S3. Right. Well, you see, many of us are blind. I don't have my glasses on today, so I'm almost right. Many of us are blind, and I claim most of us in beginning science are completely blind. It is cool, completely cool. I have this thing S3, I don't care. Right? But Hamilton is not blind. Of course, he didn't think this way. Only we think this way in a modern way. He said, well, forget it, man. Let's just forget it. Let's look at A equal the set of matrices, AB minus B bar, A bar. Well, AB, no condition. AB in C. Well, let's even write it in a good way. Let's write it here, A, B, and C2. Right? I just wrote down a copy of C2, but I wrote it in matrices, right? With respect to this unitary structure, Hermitian structure, right? Right? Well, no such that. Absolutely no such that. So, all these matrices in C2. All right, this is C2. So, I write a vector in C2b, and I say, okay, I have the matrix of this vector, so let me just write it. A sub v. And unique, it goes both ways, but I'll go to A to B. And I have another vector in C2, and I have another matrix, AW. My father's name, AW. So, yes. So now I'm going to say I'm going to multiply V times W. Well, that's stupid. That's just AB times AW as a matrix. As a matrix. You allow me to multiply two matrices together, right? So I regard this vector as a matrix, as this matrix, and this vector is another, whatever it is, and then I multiply the two matrices together. And now I just define this. This is the definition of multiplication on C2. So multiplication on C2. On C2. And this, if we identify this with C2, we write it as H. For Hamilton, and that is the quaternions. The quaternions, you have this associated, yeah, you see you have to look what the properties are, but it's everything you want. It's almost exactly the same as the complex numbers, right? Of course, you can't, well, just you have to think about it. And then you have the unit quaternions. This is quaternion. And if you have the unit quaternions, and that's a group. It's the group of elements in H. It's a set of H and H, a set of quaternions with the norm. This thing's come equipped with a norm. It's great. H squared equals 1. Well, it's the group. It's SU2. So the unit quaternions is a set of, as a group, it's SU2. Okay, isn't that beautiful? Yeah, that's really beautiful. You find these fundamental operators of, for example, quantum mechanics and so on, which people really were trying to find for many, even centuries, I think. And they are found. You know why they're found? They are found somehow because we look carefully at the notion of Hermitian structure, and secondly, we had the notion of a matrix. Matrix is a trivial notion, but imagine doing linear algebra without matrices. So somehow or another, the being able to do something with matrices is a fundamental thing. I don't know why. I try to avoid it, but I quite often do use matrices. Well, we have the real numbers, and then you complete it a little bit, and you get the complex numbers, and then you do a little bit bigger, and so these things, you get up here, and then you get something called the Cayley numbers, which are, it's very interesting. O, and these things, the Cayley numbers, these are called octaven. I don't know how you spell it, octaven. But a Cayley number. Cayley numbers. And guess what? They're somehow related to the other classic group. And the reason that the infinite series somehow stopped, the infinite series is those three things, is somehow deeply related to a classification of these division algebras. So if you're interested in the classification of the background algebra here, see the theorem of, I don't know how you spell this guy's name. Maybe I'm spelling it wrong, but that's what it sounds like. Does anybody know? Does it look right?
W-D-E-R.
D-E-R. Two D's or one?
No, sir.
I don't know.
I think so.
Maybe D, yeah, it's not, I'm talking about the bad Wetter in Deutschland. So maybe, I'm almost sure you're right, because it's a British guy, I think, or somebody, of course not a German guy. So, or Scottish probably, I'm guessing. There's a lot of science and mathematics in Scotland. Very interesting. So I think maybe Scott, you have to tell me. Anyway, you start in the middle, you hope that you can extend, everybody thought you could do this and so on, and somebody found that, and somebody found that, and then that's the end. Where you have vector spaces, where you could multiply and do various things that you want to do. Right? So it's very interesting, and it comes from considerations of the unitary group. Okay. That's issue 2. I'd be very happy, and that's the exercise here. I would be very happy if the unitary symplectic group acted freely and transitively on the 7 sphere, and then you would have the same thing. Right? You might check it. Yeah. 7-dimensional sphere. And this, of course, is a 7-dimensional sphere in C4, which is R8, and the number 8 is playing some role in the background. Cayley numbers play a definite role in mathematics, but I don't want to talk about it. Okay. So, real numbers, complex numbers, quaternions, and Cayley numbers, octave. Oh, I think if you're going to write this in English, I don't know why I put a K here. I'm completely Germanized in my view of mathematics. Of course, it's just C's. C. Maybe it's called Octaven is Deutsch, and octaves, maybe, I know octave is something in the piano.
I think it is called octonian.
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 Octonians?
Octonian.
Oh, then let's forget it. Let's go back to German. It's too complicated for me. Where is it? Octaven. Octonians. Quaternions. Well, you see what? Quaternions? Oh, probably you're educating me. Thank you. So right? Quaternions is, right, it's the four-dimensional thing, over the reals, right? And then as you say, octernions is the eight-dimensional thing over the reals. Right. Okay. Okay, but it's a very interesting thing. So that's that story. And now I want to go to a new chapter, and I beg you in mathematics and physics to sit down after I've given you this little lecture in this new chapter and really make sure you have what I'm talking about solidly in your minds. And this little situation I'm talking about is ordinary differential equations. And of course, we can talk about this stuff. And I just want to recommend very strongly the book of Arnold in this subject. So, there's one book, it's called Auf Deutsch gewöhnliche Differentialgleichungen, and in English it's called Ordinary Differential Equations. And my prayer is, if I'm going to pray, is that you read that book and try to understand everything in it. It is really wonderful. Anything that Arnold writes is wonderful. Arnold also likes the interface between mathematics and physics, as is often the case in Lomonosov University in Moscow, or Steklov Institute in Moscow and Leningrad, or St. Petersburg. These people really are close to this interface. Even the purest of mathematicians, such as Novikov and so on, are in this interface, and it's really wonderful. Right. It's really the right point of view. So I really look at this book. I love this book, and I think I don't read books usually, but I was one time in Italy, and I had the chance I was sleeping late because it was Italy, and I'd lie in bed at night and read this book, and I could not put it down. I liked it so much. Okay. Ordinary differential equation. So the simplest case is linear ordinary differential equations. ODE means ordinary differential equation. Okay? Okay. That is the subject of symmetry. Okay. So, for example, on V, a real vector space, for example, on a real vector space, for example, on a real vector space, V. So I will write there is exactly one ordinary differential equation on V. So you take A, which is an operator, so an endomorphism of V, and you think, well, that's a self-map of V, and you draw exactly one picture. You draw this picture. This is V. It's sort of an affine picture. Well, you have a point here. You have a point here, let us call it X. And, well, you have this linear transformation, so you really do have 0. And you say, I want now here we go. I want a flow. You should always think of a flow with ODE. I want a flow along a curve from X with velocity. It's high dimension, so the velocity is high dimensional vector, with velocity, which depends on where you are. At x, it's a of x. And then I move over here after flowing a little bit, and here it's at a velocity y, it's a of y. And it goes around here. The velocity is given, right? And it tells you want to flow along the curve with that velocity. Got it? Okay. So let's say, draw the picture, that's too complicated, let's draw a simpler picture. It says at every point you should have an operator which is telling you, I don't know, what velocity you should have. And what you're supposed to do is you're supposed to find a curve which satisfies that velocity. So you find a curve which starts out at a base point, x0, and satisfies that velocity. You can imagine with the way I'm explaining this, this is a subject of applied science. In every science, this comes up, right? If you don't know that as a mathematician, you are not qualified, period. Okay? I will tell you there is no course in this subject at Jacobs University, right? It's up to you to learn this, okay? So this is what is called ODE, and you're supposed to solve that. So what does it mean to solve the ODE? So solve the ODE. Solve the ODE, this easy ODE. What does it mean? Well, it means, so let's even take a base, let's call this thing Rn. Right? So a point in Rn is, we think of as a vector x1 through xn. We don't have to have, it's not necessary to call it Rn, it's just, maybe it's easier for you to understand. And what we're looking for is a curve. So I'm going to write a curve as x of t. So t is a smooth time variable, and this should be smooth. And that means that each of these coordinates is moving along in time t. That means you're moving along a curve. All right. You're moving along, you're trying to find this big curve. So solving the ODE means two things. You start at a base point, so you want to map in x, so find a curve x of t, so that x, two things, x at 0 goes through the point you want to start at. So you want to start at 0 and take off. Maybe you want to come before 0 and then go on. So you want to start there. And then its derivative is velocity, which we write as point, and you don't bother writing t all the time, is equal to a of x, where a is an endomorphism. Right? So you're getting hooked up, and what are you pointing at?
Is it somehow related to tangent spaces?
Of course. But I'm doing this in Rn, and so it's if you're learning something about manifolds and so on, the same exact description has to do with manifold. Right? It doesn't matter. As you see, it's a local matter anyway. Even on manifolds, you look at it in some coordinate charts. So the interesting case is somehow, right? Given the velocity, and your lingo of manifolds, given a vector field, and a base point in the manifold, so given this situation, that's a vector field. Field of vectors, right? Given a vector field, you want to find integral curve of this vector field. It's called the fundamental theorem of ODE, that this thing exists. It exists uniquely for finite, it exists and it is unique, but it only exists for finite time, generally. Okay? So generally, the problem of ODE, this is a simple case of linear ODE, so the general version so whatever the general version is, you have to figure it out. Solution exists, is unique, but is only local. So it only exists for finite time. Okay. I've only discussed the ODE for the linear case. Now every physicist knows how to solve that ODE, and you better know how to solve it as well. If you don't know anything. So I please beg you to know how to solve this ODE, and I will show you how to solve it here. And you will realize that you've already solved it, so you don't have to think. So I'll stop now. Let us say we define x from the endomorphisms of V to GLV, in this case over the real numbers, we define the exponential map, which you learned, some of you from me in the beginning course, and some from Keva, I don't know, from Keva, the exponential map. Right? And the exponential map, if you take something here, A, then x of A, and sometimes you write this as e to the A. I was so happy when I saw this for the first time as a student. My professor, Professor Löwner, went to the board, and for him it's a joke, but he said it's really important to write down the exponential mapping for operators. You write it down, right? Right? That's a good thing to write down. Is it not a good thing to write down? Is it not? Why is he going to write that down? Because he wants to solve this ODE, and he remembers, Professor Löwner remembers when he wants to solve this ODE, that if you want to solve this ODE in one variable, the most stupid thing in one variable is x of dot of t, one variable, equals x of t. X of t equals x dot of t. Velocity is exactly position. Velocity is exactly position. Right? You have seen that ODE someplace, I hope. Or maybe you put a number here. Let's put a matrix here in dimension 1. A. That's a 1 by 1 matrix. That's what you're looking for. It says x dot equals ax. It's the same differential equation. It's one variable. So dimension 1 in our n equals 1. I don't know about all of you, but I certainly, when I think about analysis 1, I think about this differential equation all the time. Yes? And I realize that x, say let's the initial position be equal to 1, and therefore x of t, you know how to get it. It's e to the t. Right? Isn't that true? E to the t. Yeah. You differentiate e to the t, you get e to the t. That's x point, x dot equals x. Huh? Somebody come.
I said e to the at.
Huh? Oh, I forgot the a. I'm always forgetting the a. A. Right? That's very important to keep the a in mind, because that's the velocity somehow. Okay. All right, that's interesting. So that solves that differential equation uniquely. I hope you all have some feeling for e to the t. That's it. That says these integral curves, we call them integral curves, integrate this vector field that we're talking about. So in general, my professor was really smart because he looked at this stupid example in dimensions, not so stupid, this example in dimension 1, and he said, what I expect to solve this differential equation, very elementary, he expects it. Of course, he knows, but what our great giants of the past expected, we hope that x of t equals at e to the t times a. I put the t before the a here. Solves the equation. Is the solution. And not only hope, it's true. Okay, let me summarize that. Thank you. Let me summarize that. If you're interested in the subject of linear differential equations, that subject is on this blackboard right here. That's it. And if you're interested in solving a linear differential equation, it is solved exactly like that. The differential equation is x dot equals a times x, and the solution is what you think it is, so let me write it down. Write it down. And the chalk, I think.
Or some on the top.
Give me all of that. That's maybe better because it's dry. Should be okay. So for an endomorphism on the vector space, the linear ODE, so saying that really an endomorphism is nothing more than a linear ODE, is of the form x dot equals ax, and the initial position, initial value, so it means initial value, starting point, x0 is given. And then you check, and this is very elementary to check. You just write everything down. The solution xt equals e to the ta, and now you look at the orbit of this thing. X0 is the unique solution. Unique solution. Okay. Well, that's great. That's really great. Now, in physics, for example, in physics, in the background you have a Hermitian structure on a complex vector space. Yeah. And the physics people have some interesting interesting ordinary differential equation, and it gets very interesting in the second quantization. It is really Heisenberg's viewpoint to quantum mechanics. So they're very interesting differential equations. Let's look at this here. A z of t. That's a linear ODE. Of course, I will always emphasize the initial value S0 is given as some Z0 in this vector space, complex vector space. Okay. Let's look at it in the case where V is one-dimensional. So let's look at the easy example when this thing is one-dimensional. Here's the complex plane here. This is really confusing. So okay, no, I guess it's not confusing. I may need to have a real structure here, more explicit. So if here is the complex plane, and here is a point z of t. Here's a point z, and we are interested in a one by one operator, and yes, we are interested, for example, in this is the point z, and for example, let's let this be z. No, let's not let it be z. If this is z, what is this? What is 90-degree rotation from z in terms of complex multiplication? I? Huh?
IZ.
IZ. Well, why not let this be a multiplication by I? Right? So that means, if we go here out to z, what it means is you multiply by I, this is IZ, and everywhere you go, you multiply by I. So you would hope to get a rotation, of course you do. Okay? So, okay, that's just multiplication by I. And so the solution is e to the t times a, but is equal to t times a is just a one by one matrix, which is called I. So this is e to the it. All right, you've seen this before. The solution to this differential equation is exactly this. So the solution to this differential equation, the flow of the orbits of this one parameter, this is a group. So t, this is a one, t going, we say t going to e to the ti is a one parameter group. It's a group. If you have t plus s, it goes to e to the t plus sa. It's completely stupid that this is e to the ta times e to the sa. So that's a one parameter group. And this group here, if you do this for the stupid thing, the U1 flow, we do this for the U1 flow, we get rotations here. This is very interesting. So those are the orbits. This is the orbit. If you take a base point x0, this is e to the I, this is the orbit, e to the at of x0. Right. The circle appears, the orbit appears. That's pretty interesting, right? Okay. That's the orbit. Okay. Well, let's go. Let's say what the physics tells us that here, this multiplication by I, well, maybe it's not special unitary, but it's certainly unitary. So we certainly want the flow, of the ODE should be unitary. Right? I mean, you want it to preserve, it's going to, in any model, it's going to preserve the geometry, whatever that means. So in other words, I can write, I will no longer write it, I will write x of t should be a unitary, I will write a unitary one parameter group a one parameter subgroup of the unitary group. This is general now on UN, so an n-dimensional unitary space with Hermitian structure H, right? One positive definite, of course, so you have a good unitary group. This should be a one parameter. It should be a unitary flow. It should preserve when you're moving around here. The movement is by isometries. By unitary isometries. Not just some flow and some physics. This should be unitary isometries. Here's x0, and something like a rotation. U of t x0, and this should be going around here by isometries. Okay. So you ask the question, which is the only question to ask now. Suppose you have the ODE or let's say you have a one parameter group, e to the, and now in physics, this is a terrible thing. Physics do a horrible thing to us because they will put in I, there's a reason to do this. Suppose e to the I, the one parameter group is e to the I, h, and maybe, I don't know where I want to put a t. I'm getting really tired of this. E to the I, t, a. Okay? This should be the solution. This should be the solution of the ODE. So it's going to be maybe let us not put A. I mean maybe the ODE is given by, let's put H here. Let's put H here because I put this I here in front, and the physics people will call that Hamiltonian. Yes. So this should be the solution of the ODE. So we take this should be an orbit by a unitary flow. Everything I've just said is symmetry, symmetry, symmetry. Right? I require that the unitary is an orbit by a unitary flow. That's what it should be. We're going to require that. Well, that means that this, I'll call that the U of t again. That one parameter group, U of t. It's called the one parameter group, U of t. Okay? Now this is supposed to be unitary. Let's see what that means. That means it's fixed by the involution. So it means U of t is equal, to be fixed by the involution, is U P bar transpose inverse. Right? Okay, let's do that to that guy. So we want to know the condition that H has to be give a unitary flow. So we do it. So let's put here, let's see if I can do it and not make a mistake. Oh, this T is not this T. This is a transpose T. Keep it in mind, these two T's are not the same. So that we have to put the bar in there, so that makes minus. So minus e to the I t h. Now I have to go inverse transpose, but inverse, when you have this an exponential thing, it just kills the minus sign, and transpose, a bar transpose, did I forget the bar? Oh yeah, I forgot the bar, so it's here. So it says, this has to be unitary, so this statement says, so this is not equal, this statement says, this has to be the case, so e to the I, t, h equals, apply the involution, e to the I, t, h, bar, transpose. Did I make a mistake? I don't know. Right. I apply the involution to this guy here, and I get bar, they give me a minus sign, bar on the h. Then I have to take inverse transpose. Inverse kills that minus sign. Then I have to take transpose. That just gives the transpose to the h, and so I get what I claim. So u of t is equal to, which is equal to e to h, has to satisfy this equation, and that means that h equals h bar transpose. Yeah.
I mean, when we take the conjugate, I mean, that just puts a minus in front of the I. So
That was the bar at
yeah,
first.
so why do we conjugate h as well?
So I did, I forgot to conjugate,
No, you got it.
I have it here at the end.
Why do we
No, I did, yeah.
I mean, isn't it enough when you...
Yeah, let's look at that again. So I'm applying bar, first of all.
Yeah,
That's bar. So that puts a minus in front of the I.
yes.
T is real, so it doesn't do anything. And I put a bar over the H.
Oh, we have to conjugate everything,
That's just that.
okay. Yeah.
And now I inverse, and to make it inverse here, I just kill the minus sign. Yeah? The inverse of e to something is just e to the minus something. That's good, because that's a group homomorphism. And then I have to take care of the transpose. So it doesn't do anything except transpose what I have here, H. So I did it very quickly and actually got it right. It says that this is the case. And the physicists, the physicists love these operators like this for a good reason, but they appear for me with another sign here. But anyway, these things are called Hermitian operators. There's a reason for calling these Hermitian operators. So this is the wonderful thing. You start with requirements of science, or requirements of just discussion of symmetry, that if you have an ODE, I mean, it has nothing to do with physics. If you have an ODE, and you want the flow to preserve the geometry of the ambient space, to be unitary, that means the solution of the ODE means E to this thing has to be unitary. And the physicists put that I in there. You saw when we took the bar, we got a minus sign with that I in there. And that makes signs much nicer. So they always have nice notation. So anyway, as a result, we have the Hermitian operator HT. Okay. So that's that. That's sort of interesting. So if you have a Hermitian vector space, you have the notion of Hermitian operators. And in concrete terms, that means H bar transpose equals H. The involution is then just bar transpose. Pretty simple. H bar equals bar transpose. See, no bar transpose, no inverse here. It's no nonlinear thing. You see, if it's at the group level, it has that darn inverse there, and it's very hard to calculate. So at this level, it's much easier to understand. right? So we have then ODEs on VH with unitary flow E to the I H T times base point required if and only if, so the word unitary if and only if H is Hermitian. That means H in matrix language is H bar transpose. Fixed point of another kind of involution. Very nice. That's wonderful. That's wonderful. That's wonderful. And now, a big step. Now, you have really what is the action of the unitary group UN on these one parameter groups. In other words, if you have a one parameter group, T goes to E to the IH T. I'm going to put the T in front. ITH. That's a one parameter group in one parameter group in the unitary group. In the unitary group. It's modeled on the circle. One parameter thing. So here's the unitary group. I'll draw it as a picture. It's like a big sphere. It's not really quite a sphere, but it's something like a sphere. Here's the unitary group, right? And here's some curve of one parameter group. This is the curve, e to the I, TH. It's a subgroup of dimension 1. It's a curve in the unitary group. It's called a one parameter subgroup. Check it. If you put T plus H here, it makes it a group. Right? So what you would like, this goes through the identity. And you want all the other one parameter groups. All the other one parameter groups. Okay? What are the other ones? Here's what happens. What happens? If you're a little bit naive, you want to say, well, I want another one. I want to try changing. Let's try changing this. Multiply this thing by, just multiply it by unitary transformation. U times T, I, H. Multiply the thing by unitary transformation. You know, that would be a good idea, right? But the trouble is, it moves it all the way over here. It's no longer a group. Right? You want to know what the action is, and I've talked about this since the beginning lectures, of the group on the one parameter group. It's conjugation. It has to be something like that, right? It's conjugation. So it is this. Okay? This is the way the unitary group acts on the one parameter groups. Okay? This is the action of U, again, symmetry, on one parameter group. This is highly non-trivial, because this is a highly non-trivial one parameter group and you're acting on it by one parameter groups. What the devil is happening? It's very hard to understand, right? But you have an idea to think a little bit, and you don't have to think very long. It is exactly conjugation on the generator of the one parameter group, the Hamiltonian. Okay? I mean, that's just writing down how that works, how matrix, you know, that's a joke. It's just, there's no problem. So the key action of UN is on, which let's call it script HERM. I write this in some of my papers because physicists don't like to talk about Lie algebras. And so I write on the Hermitian operators, right? Or if you wish, you might call it Ham because they're the Hamiltonians in the language of physics. And the action on Hamiltonians is of U. The action is Hamiltonian H gets mapped to U H U inverse. And now I will tell you some hateful physics notation. As you know, we know the condition the condition to be unitary is this. And so that means that U inverse can be written as U bar transpose. And physicists get very tired of writing this, so they call this U dagger. Okay? So when they write this here, they write equal to UH U dagger. And that is the action on one parameter groups. And that is the absolute fundamental linear representation of the compact unitary group UN. So let me write that. Shoot. Well, I have to write it here. So you have the action. On the unitary group on the Hermitian. So the fundamental representation of the unitary group, linear representation, that's a linear representation. And the unitary group is the action on one parameter groups, but you realize it on Hermitian operators. So the fundamental representation, and it's a linear representation, it's acting linearly on Hermitian operators, on Hamiltonians, is conjugation by the unitary. Okay. So the fundamental representation of fundamental, and this is a linear representation, of course. Linear representation of UN is on, let me call it the Hermitian operators in the, of this thing, which is the operators in matrix notation H, such that H is fixed by this very simple involution HT, i.e. the Hamiltonians. The linear Hamiltonians, these are linear, of course. Actually, if you think about them right, they're quadratic, but in this representation linear. And the action is given by U of H equals U times H times the conjugate inverse, but physics people will write this as dagger, and I think it makes sense. If you talk to physicists, it's not such a problematic thing to talk about dagger. Okay. All right, and then UH, U inverse transpose. Okay, that's beautiful, isn't it? Okay. Now I think I should stop very soon, but let me just say, remark. This is called the coadjoint representation. This is called the adjoint representation. So you know the word if you see it someplace. The adjoint representation. Adjoint representation of a compact group. This is true for every compact group. You can get such an adjoint representation. Compact group. K equal UN. That's notation. And the key is, it's too bad Oppik couldn't come this afternoon. He's interested in representation theory. Some of you also are interested maybe in representation theory in physics. The key is,
That's conjugate transpose, not inverse.
what did I call it? Ah,
I think you're inverse transpose, that's the conjugate transpose.
inverse, I'm sorry, bar transpose. Thank you. The key is, and you're going to be very excited about this, every representation, linear representation, finite dimensional linear representation, D-dimensional linear representation. If you're interested in the linear representations of this group, understand that's acting linearly on a vector space. In this case, on the vector space of Hermitian operators. Every linear representation of K can be found. In, and now I have to put quotes on this word in because it would take me a half an hour to explain to you how you find the in this representation. And this is true for every compact group. That you only have to look at this representation and you can find every linear representation. So let me just finish by using some words that you people like words. So if you want to read about that later in life, what you do here is you should identify, and which you can, identify the Hermitian operators very easily can be almost canonically defined Hermitian operators on V with the dual space of this. You have to think about it for a minute, but it's easy to make this in this situation. Okay? The representation here is called the adjoint representation. And the representation here is called the coadjoint representation. and they're equivalent. So if one thing might be better than the other, and it's amazing, but the coadjoint representation is much better. It's hard to imagine, but it's much better. There is much more canonical structure on the coadjoint representation, I think, than there is on the adjoint. I mean, it has to be the same because they're identified by some canonical morphism, but nevertheless, this is the place to look, the dual space. And there is a theory, which is very easy to understand in this case. There's a general theory which if you're really interested, I will tell you about. It would take me maybe 3 or 4 days to explain it in continuous discussions, but it's a general theory which is rather modern, but was brought to you by physics. And it's called Kirillov theory. And it's called in lay terminology the orbit method. So associated to any orbit, you know how to figure out some representation. Very deep meaning. The orbit method in the coadjoint representation will give you all representations of, depending on your situation, every compact group. Okay? That's really, really wonderful. And it's a beautiful geometry. It is a subset, if you like, of symplectic geometry. Because there's canonical symplectic structure on the coadjoint representation. Okay. So that's it. I'm going to stop with here of the classical groups, and tomorrow I'm going to do something else. Okay, thank you.